Partial derivatives, pretty cool chapter, very interesting. Your brain will love it. It's kind of like a very nice exercise for the brain. Notation, f sub x, and another notation is curly d, df over curly x. So straight d f dx was a derivative we learned before. It was not a partial derivative. So it was a final derivative, not partial, total derivative. Versus partial derivative is a curly d and x, like so. International people agree on that. It's very nice. You see it in the books. You see it, students right now learning this in class, in calculus class in Africa, in Europe, in Australia, even in Canada. And they all have the same notation. I always feel it's fascinating how people agree on this like centuries ago. So that's pretty cool. Before internet and before trains. So if you see, we don't even write prime anymore because this notation is reserved for the derivative. So prime is now extra. Sometimes you will see prime, but that's extra. F with a small x is reserved for the partial derivative. Derivative of f with respect to x. Do you know how to write with respect fast? WRT, with respect. That's American notation. I like it a lot, with respect. Nobody else knows it though, only Americans created this. With respect to x or with respect to y. Let's see the difference. X and y, the same f, but we're taking different derivative with respect to x or with respect to y. Let's practice right away. So again, people who know this material, you should let others to play with this. Everyone should concentrate. It's very fun if we do it together in class right now, and we're gonna have some cute poll and a group work right now. Example, let's practice right away. I'm very good in teaching partial derivatives, so it's nice if you concentrate right now rather than at home later. Let's consider a function x squared y plus xy squared. We had this before in calculus 1, and then we decided, we're telling you, oh, we don't like having several variables. Let's solve x in terms of y, plug it in. Now we have everything in terms of one variable. Let's do product rule. Well, now we're not going to do that. We are fine having 55 variables if you want, and all of them mean something different. X and Y, maybe location, I always say G, gravity, and so on. T, temperature. So if I ask you to find, that's weird, lots of things. So first, let's find partial derivative with respect to x. The notation is of x, comma, y, like so. The other notation is curly d, so df over dx equals. So you see notation, x and y are inside, but I'm choosing to take derivative in terms of x. Guess. So right now you don't know the answers. If you never heard this material before, is it going to be product rule or not? So it will not, even though it's a product here. Let's see why. When I'm differentiating with respect to x, I fix y to be constant. How cool is that? When you differentiate with respect to some kind of variable, others are constants. Others are constants at that moment. And then you switch back. So your brain have to now imagine, if I'm differentiating with respect to x, that everything else are constants. Y, z, t, m, all of those are constants. And that's pretty cool. Brain will refuse it for a couple times and then actually will enjoy it. Because it's like a puzzle and your brain have to concentrate and see what is important right now and what is not important. So let's see this function. Here it is. I'm staring in it and I'm telling my brain, okay, x and y are both variables. But right now, for this partial derivative, y is a constant. How cool is that? Sometimes people assume like y equals 100 and that it makes brain to see it easier. Y equals c, a constant. I don't do it. Somehow in my brain, I just stare at this and see y is a constant, not important. X is a variable, important. If x is a variable, derivative of x squared is 2x multiplied by a constant y, not a product rule. And the second part, if we're differentiating xy squared. Derivative of x is 1. Derivative of x times y squared is 1. Exactly. Multiplied by keep y squared because it's a constant. Boom. That's like a very amazing what we just did. This is the first time we're doing it, and that is actually pretty cool. Put this in the box so you have connection between the original one and whatever we just had. This is a derivative with respect to x, thinking or imagining or fixing. All other variables to be constant. So make a note. Here, y is constant. That's going to be a good note when you will be reading this. What do you think about that? Very nice time right now to ask. Definitely interrupt me, ask me. Also, I should make someone in charge. Front row, city and address in the front row, Hannah. If I talk too fast, you should let me know. Because I do talk too fast sometimes. You should please slow down. Slow down. Okay, so it's not rude at all. There was an angry TikTok. Did you see the TikTok when a student asked a professor to slow down because there are lots of foreigners in the room, and he basically said to go and mind their own business? So all good teachers were very pissed at that video. It's very normal question to ask people to slow down. That's very common sense. So that was unusual to me to see. Now let's practice the other one. Of course, okay, the answer is doesn't have to have those parentheses. Nobody does that. It's 2xy plus y squared. So now when you look at this answer, it's actually hard to tell how did we get that. So if you now look at this answer from the original, you're like, wait, 2xy plus y squared, how did you get it? So the previous notation explains how we got it. X is a function, y is a variable. X is important, y is not important. That's how you see it, right? Now you tell me the other one. Let's do the other one. Second part. F with respect to y of x comma y. So f has two variables, x and y. We're choosing now to differentiate with respect to y. That is partial derivative with respect to y. That's the notation. Equals. And now I will write down x is a constant. We're fixing it. So everything else is fixed except y. So y is a variable, x is a constant. Now your brain have to switch, and that's actually the hardest part. To switch your brain was just convinced that y is a constant. Now you have to switch. If you have 55 variables, you have to do it with each. And sometimes 2 variables are variables and 53 are constants. That's even harder. So it's very interesting actually. Okay, so x squared times y. X is not important. Y is a variable. What is the derivative of x squared y? Can you tell me? Copy x squared, right, times derivative of y. 1 plus xy squared. You stare at it and you tell your brain, x is a constant, maybe 100 or pi. Not important. Y squared is a function. So the answer is 2yx. Yeah, let's see y. Let's do it step by step. X is a constant. Multiply. Derivative of y squared is 2y. Bless you. I feel like I need to review this little note. Let me make a note here. We're doing this. Review. Calculus 1 is when I'm differentiating 5x, that gives you 5. When I'm differentiating 5 plus x, that gives me 0 plus 1. So it's 1. Just like a quick note. A constant multiplied by a function stays because it's called a rate. It's like, I call it a sticker. It's stick to a function, so it's going to stay. A constant standing by itself, isolated, is 0. Because how fast the constant is changing, 0 fast. It's a floor. It's not increasing, not decreasing. The slope is 0. But if it's multiplied by a function, it's called a rate. 5. How fast 5x is changing? 5 units fast. Let's rewrite it. That's not really simplifying, but it's nice to see that it's actually x squared plus 2xy. International notation is to put everything in alphabetical order. So 2xy. Those are partial derivatives with respect to x and with respect to y. More questions? What do you think? Now I'll be asking you at some point to do it by yourself, but check this out. Okay, yeah, interesting. So now we finally reached the moment. I always was saying e to the x derivative is e to the x. No, yeah, not anymore. Depends how you're differentiating it. If you're taking e to the x prime, that usually means we're differentiating with respect to x. But if you're differentiating like so, with respect to anything else, t, y, g, k, who knows? Maybe k is viscosity. Then it's 0. Because e to the x becomes a constant if you choose another variable to be a variable, and x is a constant. Isn't crazy? So that's why this is a good joke. That d over dx cannot do anything bad to e to the x. But d over any other variable can. So that's the idea. Now, let's see. This is good. Now, here's an explanation. Check it out. Let me see if I should do... Actually, yeah, let's do upper level derivatives. I feel like this is a good moment to keep going. You should remember that there are more derivatives than just one derivative. That's called higher level derivatives, right? Let me move it down like so. Maybe more. Higher level derivatives are, why not to now take partial derivative of this function we already have one more time. That is called second derivative. We had second derivative before. Second derivative is acceleration if you work with distances. But now it's a partial second derivative. That's become very interesting, very confusing, but actually super fun. If you want to understand what is happening here, we're taking this function we just worked with, f with respect to x. We finished it. And now we're differentiating it again with respect to x. So notation is this, x. You can imagine it can be x. That's like 5 derivative with respect to x. But they also can be mixed. yx, y, zt. Yeah, so all of this has meaning. And all of this is happening right now. So we're going to be practicing all of this. If you want to know the notation with the curly d, it looks like that. Curly d is 2, that means second, f over dx second. Some students ask why it's not consistent where this 2 is. That's just international notation as well. It has some kind of explanation. I will show you in a second. I guess I can show it right now, but people don't write it like this. The idea is, I guess let me write down. Partial derivative of f with respect to x, and then again with respect to x. That's what we're doing here. So because it's partial derivative of x and partial derivative of x, they're kind of squaring it. And the top shows it as second derivative. Well, just remember that they're not consistent. They're always diagonally. So I'm fixing y again. Y is a constant. Sometimes people say fix y, or y is a constant. Now I need to decide where to look. I have 3 equations. The original one, a derivative with respect to x, and a derivative with respect to y. I'm looking at derivative with respect to y, with respect to x, the first equation. I'm looking at this answer. Equation number 1. It's actually says 1. I'm looking at the result of the first derivative and differentiating it again with respect to x. Derivative of 2xy, if y is a constant, is 2y or x? 2y or 2x. So now it's getting confusing. Let's carefully see it again. 2xy prime with respect to x, so I'm differentiating the circle, gives you y is a constant, say 5 or 100. 2xy prime will be derivative of 2, which is multiplied by a function. You keep it. Y, you keep it. Derivative of x is 1. 2y. 2y. Does that make sense? Try to concentrate. It's actually super fun if you concentrate right now. 2y. Very interesting question. What is derivative of y squared if we're differentiating with respect to x? 0. Did you get it? It's like e to the x, but we're differentiating with respect to t or y. It's 0. This piece is a constant when we're differentiating with respect to x, but derivative of the constant is 0. How fast y squared is changing with respect to x? 0 fast. That's how it is. Plus 0. How cool is that? So the answer is 2y. How cool is that? Put it in the box. That is the second derivative of x with respect to x. Let's quickly do the same thing with y. F, y, y. F, y, y. That means the first part was already done. Higher order derivatives always go in order. There are some examples when you can skip and guess, but usually you have to calculate all previous derivatives. So, done, outside one means new one. So I'm looking, maybe let me color code it. I don't want to color code on purpose because that's usually one thing. So finished, and then the new one is whatever we need to find. Notation, second derivative of f with respect to y. That's notation. Which means, in blue, I'm looking at the derivative with respect to y. I'm differentiating it with respect to y equals. I'm fixing x. So I'm looking at which equation? Second equation. Let me color code it into blue. Blue. I'm looking at the blue equation, the result of the second line. X squared plus 2xy. Because this is exactly what we did. We found partial derivative with respect to y. Now they ask us to find it again with respect to y. So I look at y and I see that y is a variable and x is a constant. So I'm fixing x. Fixing means x is a constant. X squared gives you 0. That's the pleasant one. X squared now is a constant. 0. 2xy, if only y is a variable, gives you 2x. Exactly. 2x. Put this in the box. People who are late, you kind of missed lots of important information because this chapter has lots of cool details. But I will try to keep saying it. Do you think we can find something more? Well, to be honest, we can keep going. We can do fxxx, we can do fyyy. But what about mixed ones? Yeah, we can do mixed ones too. What about fxy? And for you to know, all of these have deep meanings. So it's not like we're just playing with derivative to torture students. Maybe a little bit. But in general, it actually has lots of meaning. Let's find x. So let's take partial derivative of x and find the second derivative with respect to y. That's called mixed derivative. The notation is second derivative of f that was done with respect to x now will be done with respect to y. So it's in order from left to right. In blue, it will look like this. In blue, it's easier to see. Second derivative. No. The first derivative, we took partial derivative with respect to x. Now we're going to put parentheses and find new one with respect to y. How cool is that? So Finished is in blue color. New one is whatever standing after that. It goes in order, basically, from left to right. Okay, that's called mixed derivative. Which equation I should look at? That's actually the most interesting part. You need to first realize where to look. Now I have lots of them. I have like 4 boxes in the original function. Which equation from those 4 and the original one I should look at? And take derivative of that. Guess. What do you think? Blue part is what we need to look at. They asked me to find partial derivative with respect to x and then with respect to y. We found the first part. Where is it? Number 1. So I'm looking at number 1 again. I'll put it here in purple. Number 1. What am I fixing now? What is the constant? If now I'm differentiating with respect to y. X. Agree, disagree? If differentiating with respect to y, x is a constant. Yes?
So when do we know when we should fix it and when we should not fix it?
The last one. So the last part, this one. Very good question. The question is, how do we know when to fix? And what to fix? Partial derivative notation, the curly D, means it's time to fix something. What to fix? Whatever is the last one. Y says that y is a variable, you fix everything else. Right now we only have x, but we might have 5 variables. All of them will be fixed then. You fix everything else. Everything else is a constant. That's why I wrote it here. Others are constant, not just the other one. There can be many. So if it is x squared plus yx plus tzx, if I'm differentiating with respect to x, only x is a variable. Everything else becomes a constant. That's what we're doing here. So look at that. Look at that. How cool is this? We're looking at equation number 1. It's in the blue. No, it's in the purple circle over here. 2xy plus y squared. Fixing x because I'm differentiating with respect to y. Y is a variable. X is a constant. 2xy becomes 2x or 2y? 2x. Agree? Y is a variable. Derivative of y is 1. 2x is a constant multiplied by a variable. So it survives. 2x, let me write down, times 1, because y prime is 1. Plus y squared. 0 or 2y? Y. 2y. Why is it 2y? Y squared gives you a power rule because y is a variable. And before y was a constant. So the question that you asked was like, how do we know when to fix? You make a choice once. You don't change your mind. The moment they tell you we're differentiating respect to y, everything is fixed. And you keep it like that until you're done. Am I done? Yes. 2x plus 2y. 2x plus 2y is the second derivative. And it's called second mixed derivative. Oh, I see. That's why I had so much space. There's a note here. So, what do you think about that? There's one more to do. So I want to stop for a second and ask you, what do you think about that? What do you think about this? Confusing? Yeah?
Could you explain again, like for 3 and 4, how the x squared and y squared turn into 0?
Yes, for 3 and 4. Very good question. Thank you. So, 2y, let's see. This one, number 3. Second derivative of f of x with respect to x. I'm looking at the first derivative with respect to x. And then the last variable tells me that everything else is fixed. Only x is a variable. Okay. So that means I look at the y squared as a constant. It's like 10 squared. And derivative of 10 squared is 0. Derivative of constant is 0 if it's standing outside. Like so. This is why I like this note I made over here. 5x derivative gives you 5, but 5 plus x gives you 0 plus 1 because it's isolated. So how derivative is answering a question how fast something is changing. How fast a constant is changing. It's not changing, it's constant. Make sense? So there's a very popular name, Constantine. You know the movie, but actually it's a name. Constantine, and then there's a idea that the person is always stable because it's constant. The name actually says that. And then for number 4, same idea, but let's carefully look. Where to look? F prime y. Okay, here it is. F prime y. Found it. Now, y is a variable. Everything else is a constant. Okay, that means x squared is just like 100 squared. Derivative of x squared is 0. Did they answer this question? Your question? Thank you. It was really good. You all should ask questions. Questions are good. And I'm actually good in explaining this. Many people told me, so catch the moment. Last one. 6. Let's find yx. I will skip the let me write down notation. Second derivative of f. First, how to write down this new notation also. I probably should put more effort and explain that too. The order tells you what to write down. The first one tells you that you first take derivative with respect to y, and the new one tells you which one will be the new one. So first with respect to y, then with respect to x, and 2 at the top means it's a second derivative. That's the notation. So where to look? So when it's not color coded, it's just fyx. Everything before the last one tells you where to look. So this is where you look. You have to find this, or either find it in the list or find it, actually calculate it. Which formula gives you f sub y? Equation 2, thank you. Equation 2, so I'm fixing. Now, I want to differentiate equation 2 with respect to x. That means, what is fixed? Y is fixed. Fix y. Now, when I understand what's going on, I need to go stare a little bit. It's like actually staring sometimes. Add the equation number 2. Here it is. I'm staring at it, basically at the very end. X squared plus 2xy. I'm staring at it. And I've stared at it before, but with different perspectives. Now I'm staring at it. And I see that x is a variable, but y is a constant. Actually, I can even write it down like this. Some people write it down, parentheses, x squared plus 2xy, xy, differentiated with respect to x. This is the correct notation as well. This notation also tells your brain what to fix. Y is a constant, x is important, x is a variable. X squared gives you 2x, and then 2xy, if x is a variable, 2y. Mix derivatives often are the same. Let me put it in a different color, maybe like red. Mixed derivatives are often the same. There's a whole theorem actually that tells us when they're the same. 2x plus 2y. Put equal sign here. And the theorem says if a function is good, and by good it's a smooth function, differentiable, doesn't have holes and jumps, mixed derivatives are usually the same. Continuous. So, note. F of xy equals f of yx, and in higher dimensions too. If, don't do that, fyx, if f is continuous, nice function, continuous. Okay, tricky question. Let me ask you a tricky question. Can you find the third, the third derivative and the fourth derivative? Let me ask you and wait for a second. So I will not tell you. Let me give you a random one and then shock you with this. So let me change the color. So in your notes, you see that's pretty unusual. Let me put it in this beautiful blue. So find, and I'm just gonna randomly make something up, like x, y, x. Okay, you do it by yourself, and then I will tell you how to do it. You can talk to people around you if you want. F, X, Y, X. First, you have to choose where to look. And then you need to choose what to do. And then you actually have to do it. So there's 3 steps. Know where to look, know what to differentiate with, and then actually doing it, right? People like, let's fail it together. I'm sorry. I should not say that. No, it was a joke. But it was a good joke, though. So, did you get it? Can anyone tell me the answer? 2. All agree?
Yes.
Good. Okay, let's see why. Let's see. Okay. Isn't it cool? It's like a puzzle. I'm trying to be excited about it because I feel it's fun. So try your best to be excited too. Easier to learn this way. Where to look tells you everything before the last variable. So x, which is the last variable, is what to do. Let me change the color to yellow. The last variable tells you what to do. Everything before that tells you where to look. I'm gonna look for fxy. Look for fxy. Either you have to find it, and to find fxy, you find f of x, not of. F with respect to x, then f with fx with respect to y, and now you look there. But we already found it. It's equation number 5. See, we found it. It's here, number 5. And now you look at the answer. It's 2x plus 2y. 2x plus 2y, parentheses, prime, with respect to whatever the last variable is, x. And the logic repeats. X is important. Everything else is a constant. 2x gives you 2. 2y gives you 0. The answer is 2. How cool is that? And so on. You can do a very mixed one. Let's do one more. Oh, wait, let me ask. What do you think about that? Maybe you think like everyone else are too fast. Some people know this material. So if you feel this is challenging and everyone else know what they're doing, don't feel bad. It's basically some people took this class either in other colleges, other countries, or here. So don't feel bad. You will catch up literally this week. Do you think you understand this? Let's do one more. Can you erase? Thank you. 8. Random. I'm just gonna make it up. So you see I'm erasing all the notation. Oh, maybe I should not. Where to look. Look, like that. Where to look. Now, the last one is always the important one. One more example. Also in blue. How about f, y, y, x? Just random. You do it and then tell me what you got. Y, y, x. The last one tells you what to do. Everything before the last variable tells you where to look. Did you get 2? Very good guess. Let's see. Do you guys get 2? You look at it and you're differentiating it with respect to x. Step 1, where to look. Everything before x tells you where to look. That means find equation number 4. Let me check if you're right. I'm looking up. Number 4 is fyy. Yes, that's the one. fyy. For your information. For your information. Yeah, fyi. Yes, fyy. So I'm going to copy that. Actually, I immediately forgot. Number 5. Number 4. 0 plus 2x. So I'm just going to copy 2x. 2x differentiating with respect to x gives you 2. That is the correct answer. And let's do one more. Why not? 9. What is going to be f x, y, x, x? That's fourth derivative. Fourth derivative. Try to figure out. What do you think about that? And I will do one more. 0? I think it's 2. Did you get 2 or 0? It is 0. Yes. It is 0. Let's see why. So everything before, now I will not put parentheses anymore. I will just highlight this. Everything before the last variable tells you where to look. I'm looking at the equation number 7. 7. And then last variable tells me what to fix. Fix everything else except x. X is a variable. But it doesn't matter. It's derivative of 2. Doesn't matter that you're differentiating it with respect to x, y, z. Who cares? It's 0. So now you can imagine I can do f, x, y, x, 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 or x, y. Doesn't matter. It's still going to be 0 because we know where we're looking at. We're looking at 0. Derivative is 0 is 0. Blah, blah, blah. So now our highest derivatives will be 0 as well. That means we reached the constant level. So remember, if you're talking about distances, the first derivative is velocity. The second derivative is acceleration. The third derivative, and actually higher level derivatives, they do exist. Do you remember the names of those? I teach it in Calculus 1 class in, say, where's the good one? I think this one. Derivatives. And we call it higher level derivatives, right? So derivatives, basic rule, just let's do, not sure where exactly. Remember, so we're going to do chain rule today and everything. So this is what we did today, but we're taking it into upper dimensions. How about that? How cool is that? That we're taking what we learn, these properties from Calculus 1 class, and we're taking it to 5th dimension, 7 dimensions, and so on. Here it is. So this is what I like to teach. Look at that. If y is a distance, first derivative is velocity, so we found it. But now you can find velocity with respect to different variables. If you have 17 variables, and we ask you, find velocity, you're like, wait, with respect to what? Velocity of gravitational forces, velocity of the distance in the y-axis, velocity of the temperature changing. So if you are jumping up, there's a gravitational forces pushing you back down. There's a temperature change in your lungs versus your other body. Temperature is changed. There is pressure inside of your lungs and heart and vessels are all different. So when you ask, find velocity, the answer should be with respect to what? My brain, my lungs, the temperature, gravity, my position. That's why it's so complicated. Upper dimensions answer more questions. So one derivative, first derivative is velocity, second derivative is acceleration. Do you know what the third one? The third one is Jones. The fourth one is a jerk. That's official physics terminology for you to know. So don't be a fourth derivative. That's a popular joke. The fifth derivative is a crackle. And the sixth derivative is pop. Very interesting because how fast you're changing. You pop. That's how fast. And the seventh derivative is log. I took it from Wikipedia. That's usually physics majors are having fun, basically. So now you know. You don't have to know it, but now you know. At least know the fourth derivative. Don't be a jerk. Now, going back to our class. You see how I'm jumping between calculus classes? How cool is that? Okay, let me explain you a cool idea behind all of this. So definitely now you know the meme. This is very famous. The meme is e to the x now can be 0 if you're differentiating it. It's not necessarily e to the x, and so on. Now, here's the idea. I have lots of cool animations to show you. I would say the idea is so phenomenal that it'll be nice if you try to understand it. The idea is derivative with a slope. At the point, it will be slope at the point. But then with respect to what? When I say we're fixing stuff, that's literally what we do. If I'm differentiating with respect to x, and this is the surface. Remember we're working with surfaces? Last time I called them little ghosts, right? It's like a classical representation of a surface. Everyone draw it like this. This is a surface. It has maximum, it's decreasing down, blah, blah, blah. Now we're trying to find derivative with respect to x. So that means you don't have to write this down. I'm fixing y. Fixing y means y is a constant. Actually, everything else is a constant. Y and z. So y is here. This is y, as you can see on this graph. That means y now is a constant. For example, 10 or 15. That is why this becomes a constant. This is the function f of x, comma, constant. If you don't see, let me zoom in. A function is called f of x, comma, constant. You can call it b, m, doesn't matter. It's y that is constant. And now we're creating this graph now because we're slicing it with the plane, imagining that y is constant. And now derivative of that gives you slope of that specific partial derivative, slope with respect to specific variable. That is why, I'm not sure if I convinced you, that is why I feel like visual learners, they need to see something moving around. So this is exactly what I'm talking about. I'm fixing y in this case. Y is a constant. So now plane is slicing the surface, and when it's slicing it, it gives me some shape, and then derivative will tell you the slope of that shape. Because the surface is three-dimensional object, when I ask you how fast the shape is changing, you should ask me, wait, with respect to which direction? North, east, east, south? That exactly means to fix some kind of variable. That is what it is going on. Let me show you more. I feel like that's not enough. Same idea here. This is a surface, 4 minus x squared minus, now it's jammed. Oh, this is good. This is a surface 4 minus x squared minus 2y to the 4. They ask to find at the point 1, 1, 1 a derivative. Yeah, but which one? We have two variables. So this is x now in this graph. You see, you have to be careful with the graphs. They always mix them up. So it's actually pretty classic, unfortunately. We're fixing x. When we fix x, that gives you a plane. The plane cuts through like a knife and gives me this line in blue. And I'm finding derivative at 1, 1. When I'm fixing one of the variable, I'm decreasing a dimension. That's actually very important comment to say. Did you hear me, people? When I'm fixing some kind of variable, one variable, fixing means that variable is a constant. I'm decreasing the dimension. I used to have x and y and z. That's 3 dimensions. The moment x is a constant, with decreasing dimension, now I have 2 variables instead of 3, and so on. So that from 3 dimensions, it took me into 2 dimensions. This is parabola. It's parabola if you look at it from the front. We're asking you to find derivative at 1, 1, 1, so we know what it means. It's a slope, it's a tangent line, derivative, it's a slope of that tangent line. Positive increasing, negative decreasing. So if they ask you, this 3-dimensional shape called a surface, increasing or decreasing, you should ask, wait, which direction? It's increasing this direction, but then it's constant this direction. Seems like it's flat over there, right? So direction matters. Are you hiking from here? Then the hike is hard. The slope will be very high. It's a hard hike. But if you're hiking here, which is like the top of the mountain and it's pretty flat at the top, then the slope is close to 0. It's an easy hike. That's what we're talking about. And the other one, if I fix y, then I'm getting this kind of slice. Imagine it's a knife. Slicing it gives you 2-dimensional object. The 2-dimensional object is in red, and I'm finding the derivative at this point, and it will be different number and different derivative, different slope. Animation. No, that one is dead. Some links got deleted. It's fine. And this one. Let me try to move it out. This shows you nice picture of different slicing planes. See, if I fix y, Then I'm taking this plane and cutting it down. Because y is fixed. Y is like 7. It's fixed, means it's a number. Then I'm taking a plane, y equals 7, cutting it through this surface we have, which is this like a saddle kind of looking shape. That gives me this object, two-dimensional object in this case, and you find derivative of that. If I'm fixing x, then it's this kind of plane called x equals a number, right? X equals a constant. Slicing it through, it gives me a different shape. It's not the same. This is a parabola looking shape. The previous one was like that. See? How cool is that? So the slope will be different at the same point. Do you understand that? Or do you have questions? What do you think about that? Very cool theoretical idea here. So let's see. I have a fun joke. It's a pun. I'm not good with puns, but someone gave me this pun, so I don't know if you're gonna like it or not. Let's see. Welcome to the master sword of calculus. That is true. It's sword because it's slicing, and it's very important. The one that will help you survive your multivariable adventure. That is true too. Partial derivatives. It's partially derivatives, but a whole lot of fun. I don't know. So my friend gave it to me, and I'm not sure if it's funny or not. Puns is not my strength. But did you get it? Did you get it? Anyway. Do you know that I have a favorite pun? My students know my favorite pun about the pirate. Do you remember my pun with a pirate? Okay, if you know my pun, don't answer the question. Puns are very hard to learn for you to know. When you're a foreigner, pun is like the highest level of understanding of English language, because it messes up with language, and the local culture joke. So that's very hard to understand, very hard to memorize. So my favorite one, if you know, don't say. What is the pirate's favorite letter?
R.
No, it's the C.
Oh.
See how clever is that? That's my favorite one. I learned it, I know how to say it, and I'm very proud of it. Okay, this is good. Let's practice more. So let me show you. This is what we did. Second derivatives. Now you have a good table. I want you to have good notes. Let's practice more, and then you will do it by yourself. Okay, let's do it. Write down the form of the function x e to the y z. Chain rule is happening. Yay. Chain rule. It's time for chain rule. Chain rule will be very important. Chain rule in upper dimensions, extremely cool. I think you will like it, but maybe not. So let's try to practice finding partial derivatives, all kind of them. And you should do it by yourself, because that's a nice practice in general. The function now has 3 inputs, x, y, and z. It's a 4-dimensional object. Output is f. Input is 3 variables, x, y, and z. It's a 4-dimensional object. For example, what is the temperature of your body at location x, y, z? So that's a coordinate. At that location, the temperature is 75 degrees, and so on. So that's what a 4-dimensional object can be also seen as a 4-dimensional quality of something. Temperature, gravity, color also. Let's practice finding the... This is from your homework, by the way. Many of those are from your homework. Partial derivative with respect to x will be... practice to write it down. You don't have to write down the curly ones, but it's nice to practice them. Curly f with respect to x. That's what they mean here. Sometimes, and then people just say f prime x or parenthesis x. So we look at the original function and we see x as something important, everything else is a constant. We fix everything else. In this case, we fix y and z. Y and z are constants for the first question. That's why I like to say everything else. There's too many to mention. What if it's like 55 of them? No, everything else is a constant. Only x is a variable for this case. We are fixing the plane and slicing the object. We're decreasing the dimension here. So x times e to the yz. Is this a product rule? No. The product rule is when the function is multiplied by a function. It will never be a product rule for the first derivatives because x will be a function, everything else is a constant. X will be a constant, y is a function. X will be a constant, y is a constant, z is a function. They never have function times function. So it's never a product rule, actually. It might be chain rule, but not for the first answer. If x is the only variable, then x is multiplied by a constant. It is 1 times e to the yz. That is pretty complicated, so ask me. Ask me about that. X is a variable. E to the yz is fixed. It's like 10. So 10x prime gives you 10. So that keep the constant. It's e to the yz. People are talking. Do you help? What do you think? Let's try next one. 2. 2 is curly derivative, partial derivative with respect to y. With respect to y means, that's too low. Let me move it high. Don't yawn. Are you kidding me? This is so interesting. I feel it's very interesting. Anyway, and it's also contagious, so don't do that. We all know it's contagious. Now, look at that. Look at this in red. Look, let me zoom in. Stare at this function. Stare at it. And tell your brain, okay, forget about the previous problem. Tell your brain that. Do you talk to your own brain sometimes, right? Like, I do. Actually, I talk in several languages. That's the problem of immigrants. Sometimes I talk in Russian, sometimes in Ukrainian, sometimes in English. Very confusing. And I also have dreams in 3 languages. Super tiring. You wake up very tired. Because your translators keep working. It's super annoying. Sometimes I talk with some of you in my dreams, like, where's your homework? And of course I'm talking in English. So now I'm translating something while I'm trying to rest. And I'm waking up super tired. And it's a curse, basically. Multi-languages is curse. So you tell your brain y is a variable because we're differentiating with respect to y. Everything else is a constant. So imagine x is 10, z is 10. For example, doesn't matter. So what is the answer? Zx e to the yz. Agree, disagree? Let's do it step by step. Very interesting. Let's do it step by step. Very good job. X is multiplied by a function. Y it's a function, but before it was a constant. Actually, that's a good note to make. Before, this was a constant. Now, e is having a variable in the exponent. So now it's a function. X, let's do this. X is a constant multiplied by a function. E, let me actually write down this. I feel like it's a good idea. Prime y. You see what we're doing? So, x is fixed. It's a constant. Let's keep it outside. Now let's differentiate e to the yz, knowing that y is a variable. Equals, just like you said, x times derivative of e is going to be that same thing. So copy. You always copy when you differentiate exponential function, not the constant. So I'm copying it. Before, e to the stuff was a constant. That's why it wasn't the same. But here I'm copying it times chain rule. Derivative of the function inside. And the function inside is yz. And now you have your brain asks you, wait, what is derivative of yz? And you tell your brain y is a variable. Yz gives you z. Good job, you see? Chain rule. Let's do a note. You love chain rule. Chain rule. I usually teach chain rule in Calculus 1 with Russian dolls. What a surprise. Because it's a function inside of the function inside of the function. And you can unfold it. It's exactly what chain rule is. So let's review. E to the 5x prime is... Oh, now it's not space. Review Calculus 1. So you see, we're taking Calculus 1 into multivariable calculus upper dimensions. E to the 5x prime is copy multiplied by the derivative of the function inside. And the function inside is 5x. So derivative of that is 5. Review. This is a beautiful Calculus 1 review. Channel will be everywhere. Review. Yes. Okay, did you do it by yourself, the last one? I'm very slow on purpose. Did you do it yourself? Do this one by yourself. I'm looking, let me write it down. Now I'm using z as a variable. So df with respect to z. Small notation, short notation is fz. In the future, you will see even dot. There's a dot z. It will have a little bit different meaning, but it's partial derivative as well. And that's in upper level classes though. You look at this function and you know that z is a variable, everything else is a constant. I stopped writing this down. Fix, in the previous one we fixed x and z. Now z is a variable, so I'm fixing everything else, x and y. Fix x and y. X, y are constant. If your brain doesn't like it, put some 100 in x and y. Equals x, we're copying it again. Now I'm taking derivative. Oh, let me write it down. E to the yz, the same thing, but with respect to z. So now I know z is a variable, y is a constant. The beginning is the same. The beginning is the same. We still copy. We copy e, so let me do. X stays outside because it's a constant. E to the yz is copied because derivative of e to the x is e to the x, whatever. E to the f is e to the f. And then chain rule says times the derivative of the function inside. Copy. That's chain rule. What is derivative of yz with respect to z? Y. What do you think about that? That's chain rule for you. And you can imagine we can find other derivatives. Can you find me fxx? Fxx. What the heck is that? 0. Yes or no? We're looking at, so the first part tells you where to look. Okay, fx, I'm looking here. But it doesn't even have x in it anymore. So it's a whole thing is a constant, 0. Wow, that was convenient. How about fyy? That's not that simple. fyy. Sometimes you can write down like this. I'm looking at the second equation, which is just like you mentioned before. You can rewrite it in alphabetical order. fxz e to the yz prime, and then I make a note. I'm differentiating with respect to y. xz squared e to the yz. Amazing. Let's do that. Slowly, x and z are constants. Y is a variable. So you have to tell your brain, forget everything you learned before. Now y is a variable. And then your brain just wants to eat something. So that's very uncomfortable. But you have to try. Then y is a variable. Copy exponential function times the derivative of the function inside. You keep reminding yourself y is a variable, derivative of yz is 1 more z. So z is multiplied by z, gives you z squared. Not too bad. What do you think about this? What do you think about this? All of that. Huh? It's fun. Like you right now, you might not agree that it's fun, but it is. You have to trust me on that. It is because it's very logical. There's no tricks here. Like you just need to kind of open your mind. At first, many people have this struggle. So this is nice table. You don't have to copy it. At first, people have struggle and their brain refuses all of this. Too hard, too complicated, lack of motivation. But to be honest, if you open your mind to have many variables in front of you, this is when it gets super fun and interesting. Let's do one more. Implicit differentiation, we're going to do it on Thursday. Oh, yeah. That's going to be fun. I don't want to do it now because I think you will not observe it well. This is from your homework number 5. F is z arctangent y over x. So beautiful. So beautiful. And then we find different partial derivatives at 2 minus 4. Very interesting. Seems like we will have chain rule, but not always. Which derivative is the easiest one? F with respect to what? Z. You see? If I'm differentiating with respect to z, all this is arctangent of something, has no z in it, that's a constant. So actually the last one is the easy one. This is the notation for C. Derivative of f with respect to z, parentheses, at 2 minus 4 is, let's first find it. Z is a variable, arctangent of y over x is a constant. So it's just going to be 1 times arctangent of y over x. That's the answer. And then the notation is a bar 2 minus 4. It means at. Bar means at. And then you're a little bit confused. What the heck is going on? What is 2 minus 4? That takes you to the beginning of this class when we start learning Oh, actually it's 11.1. Beginning of this chapter. You can take a pencil, I highly recommend, and write down this is x, this is y, this is z. Many of us are visual learners, so somehow visually see the names helps the brain to plug correct numbers. You plug, what is the answer? I don't like writing arctangent. Oh, fine. Arctangent of 2 over 2, right? 1, exactly. Arctangent of 1. Which is, by the way, what? How to know arctangent? Angle, tangent of what angle gives you 1? That's how you answer it. Hear it again. Tangent, yeah. Yeah, exactly. Tangent of what angle gives you 1? There's an angle called pi over. There's several of them, but inverse functions are fixed between angles. So that's the thing. Let's see. Questions? There's one more thing I wanted to do. Albert, seriously, you're sitting in the forum during the class. That's hilarious. But there is indeed a question in the forum that was very interesting. So I left you this. This is also from your homework. I just screenshotted it from the homework. Can you find derivative of this W? It's a 4-dimensional object. Inputs are R, S, T at 1, 0, 0. Can you do that and vote? Let's do that. That's going to be the last problem for 5 minutes.